So as students, we're faced with a common occurrence in the classroom. The professor goes to the front of the room, is writing a formula, deriving an equation on the whiteboard, and as he's doing this, they're blocking everything on the whiteboard. You can't read it. So as students, what do? We can either wait until the professor moves away from the whiteboard, and then we furiously scribble down our notes, but when we're doing that, we can't actively listen to anything else the professor is saying to us or explaining to us. So what normally happens as soon as the professor steps away, out come all of the cell phones. We take a quick picture of what was on the board so we can look at it later, but while we're doing this, the entire flow of the classroom is disrupted. The professor is distracted, the other students are distracted, and it just doesn't really work. So one option to fix this out there is smart boards. The problem with a smart board is they're very expensive, they're stationary, and for a university campus with hundreds of classrooms, it's just not economically feasible to install these in every single classroom. So what my team decided to do is devise a device that attaches to the back of a dry erase marker that allows you to copy what you write and send it out to the... My name is Ryan Wilkerson. We have Todd Martin, Taru Verma, Andres Alvarado, and Angel Ortiz, and we are Team Link, and we decided to make a whiteboard data recordation device. Now the device is very simple. It attaches to the back of a dry erase marker, and it does not interfere with the natural writing habits of the user. So you just go up there and write as you normally would, and it's not bulky, doesn't hang off, it's very comfortable. Now as you're writing, the brain of the device is the Intel Edison dual-core CPU. What that is doing is taking all the data recorded by our sensor and storing it so that we can translate it into an image file. The sensor that we're using is a SparkFun 9 degrees of freedom inertial measurement unit. And this has a triple-axis accelerometer, a triple-axis gyroscope, and a triple-axis magnetometer that takes in data so that we know the positioning and the orientation of the marker as it's being used on the board. Now, once you're done with all that, you've written all these beautiful equations on the board, you just have to take the device, hook it into your computer, and our translation software will run all the data through and create a readable and recognizable image file that you can share with other students. You can email it to maybe members of a meeting in a business setting, or anybody that needs the information that was discussed on the whiteboard. Now, after that, I'd like to open up to any questions that y'all have.
How do you track changes over time, right? Because your professor is going to have a limited amount of whiteboard. You're going to write over that 3 or 4 times during the lesson. How do you control for, is this one image, this is another change, is this a different
So in a classroom setting, typically you're set up with multiple different boards. And in a like 2-market situation, we would have a way where you could activate it until you're done with this board, and then you get a fresh canvas that you're working on. So that as you go to different boards, you're starting fresh every time, and it tracks all that information so that it can produce multiple PDFs or whatever image file you want so that you can share all of it.
Would you be able to differentiate if you go back? Because sometimes you go back to something earlier.
So that's one of our stretch goals actually, is that you could go back and maybe erase or make changes. Once we actually build the device and start testing it and doing the iterations with the software, we'll see what tweaks we can make with maybe different colors once you go back. For our proof of concept, we'll be using one whiteboard with one through. It would take looking at the code and going through the software to really develop all that, which we'll be doing next semester.
How big is that device that you can attach to the marker?
I have that right here. It's the size of it. You want to check it out?
So this attaches to the marker itself?
We're going to build like a receptacle
Right.
for it that attaches into where the cap of the marker normally goes. So then you could just attach that in just like you would a cap.
So you're making a sketch of how
So as you pick up the marker, move the marker around, we're looking at several different ways to tell the device when to save and mark that data for translation. Because when you take the pen away, I mean, all of our professors do it. They talk with their hands and are moving it around. So we want to use either the z-axis of the accelerometer to know when it's within range that it's marking. And then as it's moving, when you pick up, it'll move out of that range and know that you're making a new line. And we're looking to do a way to calibrate it to the size of the whiteboard so that it knows where on a whiteboard that it's actually positioned.
So it will have to be a calibration. And
Yes.
then you go, okay.
So we are planning to, So we are planning to have a very short, say 30-second calibration sequence, or what you can do is hold the marker perpendicular to the board and just really quickly draw some predetermined shapes at the edges. So what it would do is give the software an idea of the board. So that would help us identify the area in which we were writing. And in addition to that, we'll have some accelerometer and gyroscope values which would indicate the maximum length that the marker can be from the board. So if it's anything beyond this, that means it is not going to detect, it is not going to write. Anything like this, it'll start recording.
Have you thought about the use of multiple markers, like different colors on the board, or are we just going for one color right now?
Right now, we're going for one color, but having a selector for 3 different colors to use, because I know many professors, especially doing circuit analysis, they like to have different colors for all the different currents and voltages and all those different values. So that would be something that we'd look for with just a button indicator for a few different color choices that you could use.
What's the software platform you're doing all this signal processing on?
Okay, so we have the Intel Edison running a Linux distribution called Yocto, and on that we are planning to write C code, because A, it'll be very fast, and B, it'll be really fast, and it'll be really easy to interface with all our inertial measurement units if we decide to go beyond one. We can easily communicate via I2C or SPI interfaces. And then once we have that, we are planning to use an open source software like GNU Plot, which can take a normalized set of values and plot it over a 2D axis. And then we plan to develop a common library so that depending on our application, we can either have the translation done on the device itself, since it has the capability, or we can move the file to a companion app on a desktop and use it to convert.
So your IMU is right now at the bottom end of the marker.
Yes.
Have you looked? Is that a good spot? I could see where it wiggles a little bit more. Or at least I can see my hand right on the board and I wiggle it, which could create that problem. So have you looked into possibly having the processing side at the bottom and maybe the accelerometer, the 9 degree of freedom accelerometer in the front?
When we actually have the device really finalized, we're going to look at different, because the receptacle will be 3D printed, so we'll be able to look at several different iterations of how we want it. So to make sure, the major thing is that it doesn't interfere with the writing of the user. So if it's at the front, that just goes over the cap with a spot for the marker tip to go through. If it's on the end and it actually extends down on the sides to make it a little bit more balanced and is rested in your hand a little bit and forces the user to hold it a little bit more still than maybe somebody would normally. Those are all things that we're going to look at when we get into the 3D printing of the device next semester.
Have you determined the error rate from your device?
The error rate will come when we actually do the software translation. We started looking into all the different modules for that and what all we will need to do for the software. One of the bigger issues is drift, and if you want, I can explain a little bit more about drift as you're writing.
But you have a target, if you establish a target, I think 90% recognition.
Our target is actually just is a recognizable image. Whether or not that's 90 to 100%, it really, as long as it's visually readable, that you can actually look at it and see what it is, that's our target. We don't have a percentage metric that we placed on that. Just it's one of those, if you can read it, you can read it. If you can't read it, it doesn't work situations.
Are you trying to interpret what's on the board? So, for example, are you trying to interpret that I was typing U followed by T followed by D, or just repeat the shapes that I'm doing?
It's just repeating the shapes that you're doing.
So you're not trying to interpret what?
Yeah, it's not. The translation software just converts all the data points into the image file. It doesn't try to do it in a typeface or anything like that. It's just trying to give a perfect, or as close to perfect visual representation as we can get of what was written on the board.
But I think in general, it would be nice and useful to have a number. So you can tell this is such and such a number. So this is engineering place, not just qualitative description, probably people would prefer private number, any number, to describe the quality where you are.
So the number would vary with the size of the board with our current approach. And what we aim to do is be able to normalize value. So what we would have is the size of the board, which we'll get through the initial calibration sequence. And from that, we can run multiple tests, and we can, to improve the accuracy, we can probably use something like Kelvin filters, or we can use multiple devices which can be placed together, and then use simple message passing algorithms to communicate between them.
Runtime for that device.
The life of, so our target is 1 hour. We found that as geared towards the classroom setting, most of our classes are an hour to an hour and 15 minutes long. Anytime over about an hour, you start losing people's attention span. You sitting there and just listening to somebody for an hour, it gets very difficult to maintain good listening. So our minimum goal is 1 hour battery life.
All right, any more questions? Then we can thank the team.